Hello guys, in this video I'm going to solve a problem related to insulation design. So let's start. In the given statement, the figure shows the 50% breakdown voltage dependency on gas pressure. So on the horizontal axis we have pressure, and on the vertical axis, as you can see, we have 50% breakdown levels. um, for a coaxial SF6 insulator. So here you can see this is our conductor and insulator assembly. We have conductor surrounded by the insulator, which is SF6 insulator, and the pressure in this SF6 gas is um, is controlling the breakdown voltage, as we can see on the graph. So the structure was originally designed for 6 bar. However, it became apparent that it wasn't economically efficient to design the system for such a high pressure. For this reason, pressure was decreased to 4 bar. Design the structure again so that 50% breakdown voltage and ratio D over D remains the same. Okay, what does it mean? It means the ratio of our outer diameter, capital D, and the inner diameter. After we redesign, this ratio must remain the same. Not necessarily the absolute values of small d and capital D will remain the same. Obviously, they will change because we are redesigning the geometry, but the ratio of capital D over D must remain the same, as well as the 50% breakdown voltage. So the breakdown voltage, whatever it was at 6 bar, now the breakdown strength, breakdown voltage must remain the same at 4 bar. And so we need to determine the new capital D and small d parameters. Also, we are given another condition, which is assume the breakdown field strength Emax, okay, remains constant with constant pressure. What does it mean? It means before changing the modification, whatever electric field strength we have at 4 bar, it must remain the same after we change the modification, after we do the modification in the geometry, after we change the dimensions of our insulation. The electric field strength E must remain the same at 4 bar. Okay, so now let's summarize. What are we given? So before modification, before modification, let's suppose our pressure E is equal to 6 bar. That's our operating pressure, and we have 50% breakdown voltage U50 at 6 bar. We have a certain value, okay, and we have D by capital D by D. We have certain values, okay. And after modification, our operating pressure will be 4 bar, okay, and our 50% breakdown at 4 bar must be equal to the breakdown strength before we did the modification. So that should be equal to, so this is after modification. So this should be equal to U50 at 6, before modification. This is after modification. This is before modification. After modification is represented by bar, u bar. Okay. Now before modification, there is another condition. If we read this last statement, last sentence of the given statement, whatever our electric field we have at 4 bar, okay, electric field, maximum electric field strength at 4 bar must remain the same. So E dash at 4 bar must be equal to E must be equal to E at 4 bar, which means before the modification. Okay, so we have these information given, okay, and we need to solve for new values of capital D and small d, which we call them d dash and small d dash, capital D bar and small d bar. So we need to find these values. Okay, so let's start with our formulas. So we are given. So first of all, let me find these values. U50, U50, 50% at 6 bar. So if I let me label the graph as you can see here. So U at 6 bar, you can see here U at 6 bar is equal to approximately 370. So let's write this value. U 50% at 6 bar is equal to 370, and the units are kilovolt. Okay, and we have capital D 54, we have small d 20, so this is 54 by 20. Okay, now E at 4 bar we need to calculate. E at 4 bar, remember the formula we studied, we discussed when we discussed cylindrical insulation. So E is equal to U over R ln of RO over Ri. Okay. Now here at 4 bar, so we are going to write E at 4 bar will be equal to U at 4 bar, and we are talking about breakdown field strength, as it is mentioned here. So breakdown field strength is the maximum field strength at the surface of the insulator. At the surface of the conductor. So that means here we are going to take 20 because the diameter of the conductor is 20. So we are going to take here radius will be 20 by 2 multiplied by ln of RO. Outer radius is capital D by 2 and inner radius will be small d by 2. So now U at 4 bar, so this is 4 bar, Okay, U at 4 bar is approximately 280 volt. Okay, so we are gonna put these values. So 280 kilovolts divided by 10 millimeter, and natural log of capital D is 54. So 54 over 20. Okay, so that will give us, if we solve this, we will get approximately 28.19 kilovolt per mm. Okay, so now this was before we did the modification. Now our condition states that after the modification, our electric field strength, breakdown field strength, must remain the same. So new electric field strength at the surface of the conductor will be same as the electric field strength before we did the modification. That's our first condition. Okay, now let's write the equation for after the modification at 4 bar. So U bar 50% at 4 bar. We know the relationship for the voltage is equal to, we discussed when we talked about electrostatic fields in cylindrical assembly, that was equal to, so let me write the general formula first. So general formula for the voltage or the breakdown voltage, UB is equal to Emax or EB RI ln of RO over Ri. Okay? And then in terms of diameters rather than radius, so it will be EB, our inner radius is d by 2 in our given assembly. So inner radius will be half of this, which will be small d by 2. So it will be d by 2 ln of capital D by 2 over small d by 2. Divided by 2 will be cancelled with divided by 2, so we can simply write it as capital D by small d. Okay. Now we are talking about after the modification. So UB bar at 4 bar, okay, after the modification. So that means we're going to put bar on everything to differentiate between before modification and after modification. So EB bar at 4 bar, D bar, and capital D bar and small d bar. Okay, so now we're going to put the values. Let's see what can we find out from this equation. So U4 bar is equal to UB at 4 bar is equal to, according to the given statement, is equal to U50 U50% at 6 bar, which was equal to 370 kilovolt. Okay, because our condition stated that breakdown strength must remain the same after the modification. So whatever breakdown strength we had before we did the modification, because we were operating at 6 bar, so we had this much breakdown strength. Now after the modification, even though we will be operating at 4 bar, still our breakdown strength must remain the same, or the breakdown voltage must remain the same. So UB at 6 bar must be equal to UB at 4 bar after the modification. So this will be equal to 370 kilovolt. And then also we were given in the last statement of our question, we were given that assume the breakdown field strength remains constant with constant pressure. That means at 4 bar, whatever breakdown strength we had, now because we are operating at 4 bar, we must have the same breakdown strength, breakdown field strength. So we must have 28.19 kV per mm. Okay, and then multiplied by d bar by 2, because we don't know the value of that. Okay, and then ln of, now here also in the question we were given that the ratio of the, also in the given statement, the ratio capital D by small d remains the same. Okay, that means our d bar or small d bar will be equal to before the modification. The ratio will be same as before the modification. So we can simply write this as we had the ratio before the modification. So how much we had? It was 54 by 20. 4 by 20. Okay. Now we have only one unknown, which is d bar. So after we solve this one, we will get d bar approximately equal to 26 millimeter. Okay. And then because we know that capital D over small d is equal to capital D bar over small d bar will remain the same, and that will be equal to 54 over 20. Okay, and that will further give us d bar will be equal to small d bar and 54 by 20, and after plugging the value of small d bar, so 26 and 54 over 20, we will get the capital D bar approximately equal to 71 millimeter. So as you can see, now our dimensions are changed. Okay, before the modification, our delta D was equal to 54 outer diameter minus inner diameter, which was 20. So it was approximately 34 millimeter. Now after the modification, delta D bar is equal to 71 minus 26, so which is 45 millimeter. Now which means the gap distance, the gap or the spacing where SF6 is filled has increased. So in order to keep the same breakdown voltage. Okay, so now I'm going to summarize these steps. What are the steps? What we did in the first step, we determined E B at 4 bar before the modification. Before modification. For this, we used UB at 4 bar. We used capital D. We used small d. These are the dimensions before the modification. Okay, and then we saw that UB at 6 bar before the modification is equal to UB 4 bar after the modification. Okay, so we use this condition, and also we used this condition that EB at 4 bar after the modification is equal to EB at 4 bar before the modification. So after the modification is represented by bar variables, and before the modification is represented by without bar variables. Okay, and then we use the expression for the breakdown voltage at 4 bar, which is after the modification. So UB at 4 bar after the modification is equal to EB at 4 bar after the modification, and D bar by 2, and ln of capital D over small d. We used capital D over small d same as before the modification because the ratio remains the same. Okay, now we saw that this one is equal to this one, which we calculated before the modification, and this one is equal to this one, which we determined from the graph before the modification, and this gave us d bar. Okay, and then from the ratio, as d over d is equal to d bar over, and this is equal to 20, sorry, this was equal to 54 by 4 by 20, and that gave us d bar. Okay, so that's all. This is a little bit tricky problem, so you need to um, understand the given statement, and then you need to follow the instructions and follow the concepts which you learned in electrostatics. Thank you.